input output organization as a part 1. There we are going to cover the topics called accessing IO devices, interrupts and exceptions. The presentation milestones as follows. The accessing IO devices, and when you are accessing the devices, there could be some exceptions will be happening, and also the intentional and unintentional the interrupts will be happening. Here we can consider the this diagram. We have processor, memory, IO devices and so on. Those will be connected to the bus between these devices, and the memory and processor. Bus will be interact and coordinate with all these devices. Multiple IO devices may be connected, the processor and memory via bus, and 3 sets of lines are there. Of course, those address, data and control signals. Each IO devices are assigned to an unique address, and IO devices of the processor place the address on the address lines, and address responds the control signal. Further, that devices and memory share their same address. One such technique called memory mapped IO. Any machine instruction that can access a memory can be used to transfer the data to or from an IO devices. Of course, here involved the simpler software. The other maybe memory have a different address access, address space compared to the previous one, that is same address. There are some special instructions that in and out to transfer the data from these devices. IO devices may have to deal with fewer address lines, and not physically separate from the memory address lines. In fact, that control signals to indicate whether it is a memory address or an IO address. The further extension of this device connection, there is a separate lines input device for which we have interfacing circuits will be there. This input device will be connected to the other device, so maybe processor or memory, that should be connected to through the IO interfaces. One such the control circuits, data and status register, and the address decoder. In turn, these connected to the bus. Bus is a collection of wire which carries some information. Such information may be address, data, or control signals. The device connected to the bus using IO interface circuits, which has the following address, data, and control. That is the decoder. Address decoder normally decodes place the address lines, and thus enabling the device to be recognized its address, and data register hold the data being transferred to the from the processor. Status register holds the information about the status of the devices, whether they are enabled or disabled or interested, and so on. That data and status register are connected to the data line, have unique address. Of course, further, the data at which rate the data transfer between these devices and this one, obviously it is slower compared to the processor, because these IO devices are the electromechanical devices. Processors are purely electronic devices. This creates the need of mechanism to synchronize the in order to bridge the speed gap between these the processor and IO devices. So that it may be program controlled IO, one such technique. Processor repeatedly monitor the status flag to achieve the necessary synchronization. The processor is a polling check. Is what are all the devices are connected to them, and whose processor are active and inactive, static, whether they are interested to communicate or data transfer. For various purpose, they are meant to have established a relation with the processor. Obviously, processor themselves has to check the status of those devices, whether they are interested or not to communicate, and further processor polls the IO devices. It is randomly checked all the processors whether any device need a service. To other mechanism used for synchronizing data transfer between the processor and memory. That is one kind, that is interrupts, and other kind is called data memory access. And this interrupts in data memory access will help us to transmit the data between the processor and the memory or with the devices by checking their status, whether they are interested to communicate with or establish the communication with this and need to transfer the data. So one such mechanism we have seen that other than synchronism came through the programming instructions, that is in and out, and various other instructions that are available maybe in the 8086 or any assembly language programming. Of course, they have some instruction, dedicated instruction to establish the communication. So the professionally or the more interesting one, the interrupt topic, will be going to be establish the communication. So in a program called IO, when the processor continuously monitors the status of the device, it does not perform any useful task. Right? It dedicated monitoring. Right? The processor is a dedicated given, that is, it's give whole intention, the whole service they given to the only checking for those processor. In the meantime, that they are not doing any computations. An alternative approach could be for IO devices. An alternative alert the processor when it become ready, does by sending a hardware signal called interrupt to the processor. So it sends a signal to the processor. So I am interested to do some data transfer, so that I need some processor service. So it will put an interrupt. So at least one of the bus control line called interrupt request line is dedicated for this purpose. There is a dedicated line is there. Processor can perform other useful tasks while it is waiting for the device to. So in the earlier task what we mean, that is a program controlled IO. So it was give a whole intention, whole the dedication to this other devices. Now this processor can do their own job. In the meantime, they can also give attention, but it not necessary to stop the continuous execution of the program. And the subroutines will be a take of this interrupt concept. Subtask consists of a set of instructions which is executed n times, is called subroutine, right? So that is a set of instructions will be sandwiched in the program, that is a small program. It called as a subroutine, right? Subroutine, that is. So here we can see that the program branches to subroutine with call instruction. And once the subroutine is executed, the calling program must resume the execution starting from the instruction immediately, right? So followed by the call instruction. It start to execute the call program must resume after execution of the subroutine. It should go back to the call program. There it has to continue its duty to execution of the instruction of the remaining, which is where it is stopped, right? So the control is transferred back to the calling program. This is done by executing the return instruction at the end of the subroutine, right? So the body of the subroutine is a begin and return, that is. So return instruction will be tells about that. So continuous of that, call instruction is a special branch instruction that performs the following operations, right? Call instruction performs the branch instruction following operations. The store the contents of the program counter into link register. Store the contents of the program counter into link register. The content of the program counter is tells about the address of the subroutine begin, right? Subroutine begin. So branch to the target address specified by the instruction. So once that contents of the PC link register and the target address, that is where the subroutine begin, so that address will be loaded onto the program counter, and it is to resume the execution of the instruction. After executing the subroutine, it may encounter the return instruction in the special branch instruction, so that perform the operation. The branch to the address contained in the link register. So link register will be holds the address of the called program where the instructions should be continue. That previous link register address contents of the link register tells the where that instruction has to be there, and from there you have to start the execution, right? So that will tell us about that. So one such example here from the diagram, we can see that program 1 contains the m number of instructions, and these m number of instructions, while executing, there is a interrupts arrive. Interrupts arrive means there is a subroutine. Subroutine means that is a interrupt service routine. So interrupt service routine will be there whenever the interrupts occur. For example, interrupts occur at the ith instruction, right? Interrupts occur at the ith iteration. During that time, the program control and all those will be suspend this program execution and store the necessary information, in the sense that some of the intermediate results have produced till the ith instruction executed. Those information will be stored safely. Then give a control to where the subroutine are, or who is the interrupt made enable, right? There we have to control has to go. So from this ith instruction, it goes to the interrupt service routine. So interrupt service routine have the information. It is the starting address of that subroutine. The 4000. Let assume that 4500 is the starting address of the first instruction of the subroutine. So as executed all the instruction, here it will be encounter the return instruction, right? So as soon as the return instruction will be encounter after executing that and knowing the semantics and syntax of that instruction, it will be came back to the called program. Where called program, so the instruction, the register I plus 1, where that instruction will be there. From then onwards, you start executing the remaining instruction with the help of the instructions, the results which are already stored there, and make use them, and with the making use them, and it will execute the next instruction till the instruction, right? So this is a diagrammically explanation. Let we see some other, that is processor is executing the instruction located at the address I when an interrupt occur, right? So routine executed in a response to interrupt request to called an ISR. So it will go to the called subroutine. For that interrupt service routine will be there. When an interrupt occur, control must be transferred to the ISR. So, but before transferring the control, the current content of that PC, that I plus 1. So this I plus 1 address will be stored on the stack of the register. Stack memory, stored on the stack memory. So that let assume that this is a stack memory. So I let assume that ith instruction address is 2000, the I plus 1 instruction is 2004. If the 4-byte machine instruction, if the 4-byte instructions are assumed, then ith instruction address is 2000 and I plus 1 address is 2004, right? So now it is before going transport to the current content of the PC, that is I plus 1 will be stored on the stack of the memory, on the top of the memory, right? So now it will go to the must saved in the known location, that is a stack memory. So this will be enabled the return from the interrupt instruction to resume the execution at I plus 1, right? So return address will be content of the PC are suitably stored on the processor stack, right? So when you go to the ISR, so that ISR will be 4500. For example, I wrote that is. So next that after encountering the return instruction, it will be come back to the I plus 1 instruction by popping up the top of the stack, that is a 2004. Treatment of an ISR is very similar to that of subroutine. However, there is a significant difference is there. Significant difference is there. So subroutine performs a task that is required by the calling program, right? So ISR may not have anything in the common with the program interrupts. So it is quite similar to that interrupts. So ISR and program that interrupts may be belongs to different users. So as a result, before branching to the ISR, not only the PC but other information like condition codes, flags, and process register, all those the essential information will be required after coming back from serving the subroutine. It come to the main program now. There it is utilized, that is. So that it will be placed safely in the processor status, that is information, and interrupted back a program, and ISR must be stored those. So this will be enable the interrupted program to resume the execution upon the return from the interrupt service routine. So continuation of this, the saving and storing the information, saving and restoring the information can be done automatically by the processor, explicitly by the program instruction, right? So saving and storing register involves memory transfer also. So increase the total execution time. It is executes the extra time is required. Increase the delay between the time and interrupt request is received. And the start of the execution of the ISR, this is called interrupt latency, right? Because the control switching between the call program to and calling program. So if the instructions are there is a pair address and there is a different addressing mechanism will be applied. So due to that, there is a some amount of latency will be involved, some amount of delay will be involved. So that delay we need to be tolerate. In order to reduce the interrupt latency, most processor save only minimal amount of information, right? So this minimal amount of information include the program counter, process status register, the condition codes, and flags information. These are the minimum amount of information is most essential, so that it planning to put safely, that is. So here there is a program execution, and any service is required. For that we have to raise an interrupt request. Any additional information that must be saved saved explicitly by the program instruction at the beginning of the interrupt service routine. It must also inform the device that has recognized the interrupt request. When the processor receives the interrupt request, it must be branched to the ISR, right? So when we are executing the program, certain device need a service. For that it send a request, that is interrupt request. For that interrupt request, it must be informed to the device whether it has to be recognized the device and provide a service immediately, that is. This can be accomplished in two ways. So that is one, some processor have an explicit interrupt acknowledgement, right? Interrupt acknowledge control signals for this purpose. Some processor have interrupt acknowledgement signal is there. So suddenly they will, for example, Intel 8085 86, they have int the signal. That signal will be go to the respective processor. Okay, we have received your request, so we will shortly provide the service. The kind of signal will be goes to the automatically to that service. But in some other cases, data transfer that takes the place between this device and processor can be used to inform the devices, right? So there is a device processor can use to information, that is okay, we will give a service for that. This is not default, it is additional information they will be sent by the processor. The further, that is interrupt request interrupts that is execution of the program and may alter the intent sequence of the events, right? Processor have privileges, that is, or by the program also you can alter the priority of the services. Sometimes such alteration may be undesirable and must not be allowed. Sometimes allowed and some not be. Example, processor may not want to be interrupted by the same device while executing its ISR. It's already providing one service to the particular device, but it is requesting one more service. It is putting one more demand. So in such case, it not possible. So straight away it will be reject that. Processor generally provide the ability to enable and disable such interrupts as a desire. That is one simple way, that is provide a machine, that is instruction such interrupt enable, interrupt disable for this purpose. So there is a additional facility will be there. So in such case, you don't want to some disturbance from the other devices for the processor. So sometimes you can make it enable. If it is enable, then the device may be put a demand or request. If it is disable, so that even if the device may put the request, that processor may not consider them because they have set the door for all the devices for the service at the certain amount of time, right? In a critical situation, it may happen. To avoid interruption by the same device during the execution of an ISR, it is obviously the first instruction of the ISR can be interrupt disable. If you are executing any ISR or subroutine, so beginning itself you have to make it a interrupt disable instruction we need to be execute. the last instruction should be interrupt enable, that is. So it means that in between this ISR execution, so there no other device can be get a disturb, no other can intensely disturb, no other device can get a the service up from the processor, so that safely we can, like a critical time or some it will prevent all the processors or any devices unnecessarily interrupting that, so that we can put a safe lock for that. They can come afterwards as soon as you complete the current task, current subroutine has completed. Similarly, the multiple IO devices may be connected to the processor and memory. Of course, some of all those devices may be capable of generating the IRs, right? So interrupt request, that is. So each device operates independently. Hence, no definite order can be imposed on how devices generally interrupt requests, right? So there is no discipline at all. There is a mismatching or randomly they are producing. How does the processor know which device has generated the interrupts? So these are some very important aspects. How does the processor know which ISR needs to be executed, right? So one processor is executing ISR for one device, and can other device interrupt the processor, right? So if two devices are have an interrupt request or received simultaneously, then how to break the tie, right? There could be a deadlock will be happening, or they are independently, those devices are keep waiting, we are getting service, those devices are getting, and immediately we may till waiting, like that. They will waste they are simply wasting their time. Consider a simple arrangement where all devices send their interrupt request over single control line in the bus, right? Single control line, it will be there, interrupt request will be sent by many processor. When the processor receives interrupt request over those control lines, how does it know which device is requesting an interrupt, right? So this information is available in the status register for the device requesting an interrupt. There is a status register of 8-bit or 16-bit. Okay, so that for example, 0th bit will be 0th device, and first bit will be first device status. Like that, there is a status register will be there. That status register has to be loaded before that when starting executing. That may be programmable. Sometimes default through the system also configurable. Status register of each device has an interrupt request queue bit, which is set to 1 when it is requested an interrupt, right? So ISR can poll IO devices connected to the bus. The first device with the interrupt request equal to 1 is one that is service, that is. The first interrupt raise the request, then that device 1 is able to get the service. Similarly, the polling mechanism is easy, but time consuming to query the status bit of all IO devices connected to the device. If not, if n devices are connected to the processor, all the device address will be there at the premise of the processor. Processor is intensely check all the device status of the, whether these first processor is interested, whether the second processor is interested, whether the second device is interested, or the third devices, or the nth device is interested. Like that, it go and check all the bits of those processor is definitely is a time consuming. It's quite difficult. The alternative one is a vector interrupt, that is the vectors we can store, and those addresses will be stored in a table. So those are called vector interrupts. So the device requesting interrupts may be identified itself directed to the processor. The device can do so by sending the special code 4 or 8-bit processor over the bus. So code can supply that by the device may be represented part of the starting address of the ISR. The remainder of the static address is obtained by the processor based on the other information, so where ISR is located. So usually the location pointed by the interrupting device is used to store the starting address of the ISR. So the priority interrupts, the IO devices organized in a priority queue structure. So if the request from the high priority device is accepted when the processor is executing ISR, low priority is denied. So the priority level is assigned to the processor that can be changed under program control also. So priority level of the processor is the priority of the program that is currently being executed. When the processor start executing ISR of the device, its priority is raised to that of device. If the device sending an interrupt request having a topmost priority, then processor processor accept the interrupt request because it is a higher priority. Processor priority is encoded in a few bits of the processor status register, so can be changed by instruction that write into the processor status register. Usually there are privilege instructions. Instructions can be executed only in the super mode. So such super mode will be given to the top priority devices. Privilege instructions cannot be executed in the user mode. Prevents the user program to accidentally or intentionally changing the priority of the processor in the super mode. If there is an attempt to execute a privilege instruction in the user mode, it causes the special type of interrupt called privilege exceptions. So privilege exceptions, so it some higher priority interrupts are going to be executed in the user mode. In such case, privilege exception will be there. So each device has a separate interrupt request and interrupt acknowledged line. Each interrupt request is assigned to different priority level. So let's consider that priority arbitration. So there is a processor. So there is a device 1 is connected. So device 1 is connected. It may send a request to the processor. If that is a request is processor is intended to provide a service for that device, and it will be sent an acknowledgement, right? So okay, I am ready to provide a service. You will get it ready for provide a service. That device maybe it want to transfer the data, or maybe read the data, or get the data. This various kind of service the device may be one required. For that, processor help is required, for which we have to send a request, and for that we will get an acknowledgement. So INTR1 it is the interrupt request from the device 1. So it goes there and it shows identity in the processor, and with help of the processor register, processor can understand and send a request to by sending okay, device 1 take an acknowledgement, I am ready to get serving. That is a priority, the base that is. So device 2, similarly device 2 have a separate interrupt request and separate interrupt acknowledgement, right? So device 3 have separate, so device P have separate. So everybody have separate request and separate acknowledged. Each IR line is assigned to a different priority level. Of course, that is, if it is receive this line sent to the priority arbitration circuit in the processor. If the IR interrupt request has a higher priority level than the priority of the processor, then the request is accepted. No doubt here. If any device is sending, for example, device 2 sending some request, it's have a highest priority, then immediately get a service. If not, what will have, that is which are interrupt request does processor accept if it is receives the interrupt request from the 2 or more devices simultaneously. In that case, the devices are organized in the priority structure. Processor accepts the IR from device with a higher priority. So each device has its own request and acknowledged line. So different priority level assigned to the interrupt request line of each device. However, if the device share an interrupt request line, then how does the processor decides the which interrupt request to accept, right? Multiple interrupt request is coming. So having the different the priority or same priority, then that case there is a conflict will be there. So such will be scheme will be polling scheme will be applied. That is, if the processor uses the polling to poll the status of the register, means you can keep on check all the processor, all the device status, whether device 1 is interested, whether device 2 interested, whether device 3 interested. Like that, it is a time consuming process, as we discussed in the previous slide, to find which device is requesting an interrupt. So in this case, priority is defined by the order in which the device are polled. So first device, if the first device with the status bit is 1 is a device whose interrupt is request is accepted, and this processor there is a daisy chain concept we will be going to be tell, that is, so device 1 is connected to the processor, and device 2 is connected to the processor, device N is connected to the processor. So device 1 will be send a request to the processor, and if it is the device 1 is sending a request to the processor, and processor is ready to provide a service to the device 1 and immediately send an interrupt acknowledgement. If the then interrupt request is a common request, so this request will be shared by all the processors, so devices. So that's why what will happen, if the interest request is coming and reaching to the processor, and the processor is ready to provide a service, and this acknowledgement go to the device 1. If the device 1 is raised the request, then it will be accepted. If not, it will propagate the interrupt acknowledgement to the next process, next device. Similarly, interrupt device 2 is raising an interrupt request and go to the processor. The interrupt acknowledgement will comes. Assume that device 1 is not risen and the device 2 is raised, and it will be accepted. Otherwise, it will propagate that acknowledgement to the next device. So this will be keep on going to the end devices. Devices are connected to from a daisy chain. That is a concept of daisy chain, that propagating the interrupt acknowledgement to the one device to the other devices and sharing the interrupt request. So this IR and IA, that is a request and acknowledge line, is connected to the form daisy chain. When the device is raised, an interrupt request and the interrupt request line is activated. So the processor is a response activates the interrupt request received by a device 1. So if the device 1 does not need a service, it pass 3 signal to the device 2. It propagates the next device is electrically. If nobody do not have any interrupt, priority, and who is which device is very electrically close to the processor, that they have always get the highest priority. Electrically closest to that processor has an highest priority. So the combining this polling scheme and daisy chain, much powerful that is. When IO devices were organized into priority structure, each device had its own interrupt request and acknowledge line. When IO devices were organized in a daisy chain fashion, the devices shared in a request and acknowledge propagated through the devices. So the priority arbitration which will receive the interrupt, that is a device 1 will be have a interrupt, that is, so device 2 will be there. Like that, the devices form a group here. So the first group we have n number of devices are in the group. Similarly, second group, third group, there is a p number of groups will be there. So they have that the IR and request line. The combination of this priority structure and decision scheme has also used, that is, devices are organized in two groups. So each group is assigned a different priority level. There is a different priority level will be there. All the devices within a single group share an IR and are connected to form a daisy chain. For example, consider the first group. So 5 devices are there. So the who are raising that, and they will get a service. If they are not raising, it will propagate to the next, that is. So in that, n groups are connected. The p number of groups are connected to the processor in the fashion of daisy chain, and this the other concept, that is a polling, that is interrupt priority. So interrupt enabling bit, that is. So only those devices that being used to program should allow to the generator interrupt request. So control which devices are allowed to generate the interrupt request. The interface circuit of each IO device has an interrupt enabling bit, that is. So enabling bit will be tells about these device device ID and their status. Then device is allowed to generate the interrupt request. So enabling bit is the device interface circuit find that is whether the device is allowed to generate an interrupt request. So that enabling bit, that processor status register or the priority queue structure of an interrupt determined by which whether the given interrupt will be accepted or not. So one more such kind of things called exceptions. So interrupts are caused by interrupt requests sent by the IO devices. So this could be used in many other situation where the execution of the one program needs to suspend and execution of the other program need to be start. So in that case, so in general there is a term exception is used to refer an event cause an interruption. So interrupt request from IO devices is one type of exception. Is also one. Other type of exceptions are the recovery from the errors, division by zero, so infinite loop, and debugging, kind of debugging. So and privilege exceptions, right? Privilege exceptions. So that user mode and super mode we discuss. In the user mode, some high priority interrupts we want to execute. So in that, normally they are not allowed, but in the privilege exceptions will be allowed. That is. So many source of errors in the processor. Example, the error in the data stored. So data stored in error during the execution of the instruction, correct? Execution of the instruction, we have syntax errors, semantics errors, so on. That when such errors are detected, exception process is initiated. So processor take the same steps as a same steps caused by IO interrupt request. So IO interrupt request, it suspend the execution of the current program and resume the exception service routine. It goes to the exception service routine, that is called ESR. Difference between the handling IO's interrupts request and handling exception due to errors. That is, in case of IO interrupt request, the processor usually completes the execution of an instruction in the progress before branching to the ISR, interrupt service routine. In case of exception, it may not so. It is a progress usually cannot be completed. It's suspended in the middle also. There is one more terminology called debugger, uses the exception to provide important features called trace, breakpoint, step execution, single step execution of program, so on. That is, so the trace mode, that is exception occurs after the execution of the every instruction. The debugging program used to the exception service routine. There is a breakpoints. Exception occurs only at a specific points selected by the user. Debugging program use the exception service routine. The privilege exceptions, I told, that is certain instruction can be executed only when the processor is in supervisor mode. These are called privilege instruction. If an attempt is made to execute the privilege instruction in user mode, the privilege exceptions will be occur. It denies that. The privilege exceptions causes the processor to switch to the supervisor mode and execution of an appropriate exception service routine. So with help of this, I hope you followed this concept of accessing devices, IO devices, and interrupts and exceptions concept. Thank you for patient listening of topic accessing IO devices, interrupts and exceptions. The reference are the Karl Hemacher and Java Kranchik, Sapwat, Jackie, Computer Organization, 5th edition, Tata McGrath, and reference book, that is a Stalling, Computer Organization and Architecture, 9th edition, Pearson 2015 edition, and the first one is a textbook, second one is a reference book. Thanks to coordinator, moderator and subject expert for providing the opportunity to make this video lecturing. For the listeners or the students who are interested to listening this, those who have some queries, you can post these queries to this mail ID related to the topic. Thank you for patient hearing.